So I guess let me just start by sort of recapping what we've seen so far. So I've given you some introductions to maybe how to think about entanglement in the continuum limit and the appropriate things there, including modular Hamiltonians, modular flow, and such. And in the second lecture, I also talked a little bit about the perturbative approach to computing these quantities in the continuum. And today, I want to sort of put those two together, and the goal is to study some form of perturbations. We'll talk about shape perturbations. And the goal is to produce a proof of the average null energy condition. So this is some condition on quantum field theory that has been discussed a lot lately, so I think it's useful to sort of go through in detail one of the proofs. And so this is proof that I was involved with Rob Lee, Onka Parika, and Huajia Wang. And the idea is to study the shape deformations of the modular Hamiltonian. So I told you why I like modular Hamiltonians, and it turns out that it's a useful thing to think about how they depend on the shape of the region, okay? Okay, in some perturbative expansion. So the starting point is we're going to consider some entangling cut, and we'll take the entangling cut to be just a Rindler cut. So that means I'm taking half of all space. And this is, of course, the situation, the useful situation, where we know exactly what the modular Hamiltonian is, and it's very powerful. And so we have some Rindler wedge associated to that in this. Okay. And this is on some spatial slice here, and here is our region A, and here is the A complement. And now let's imagine deforming the region a little bit like this. So that means that now I'm going to have B, which is everything over here. We use colors. As my, as describing the physics in this region, I'd like to think about the density matrix of this region. And then there's B complement, which is over here. And we're going to do it perturbatively, so there's going to be some function here, delta x of y, which is going to describe this shape. Okay, and so there's going to be some non-trivial shape in this direction. And so that's the situation where now I no longer know what the modular Hamiltonian is, because it's no longer this sort of geometric region. There's no rotation invariance around this surface. Okay, good. Now, okay, so we're going to perturb from A, the boundary of A to the boundary of B. It's useful to think of the perturbation as just being the perturbation of the boundary of the region that you're interested in, and this defines some function delta x of y. Now, this is one picture, and I've really sort of only drawn a deformation in the spatial direction. But as you know, in quantum field theory, I can talk about, instead of regions, I can talk about causal regions, and I can talk about the algebra of operators in various causal regions. And so I can actually deform in the time-like direction. And here the picture, I'll draw just a cross-section of this picture. So I'm not going to include the y directions, which are coming along the entangling surface. I'm just going to fix that to some constant. And then the picture is that we have some region A, which I'll draw this, some region D of A, and then we're going to perturb that region, and there's going to be some vector which describes the perturbation. Okay, so it's just a vector in the transverse directions, so it's sort of two, because everything is always codimension 2, it's just a two-dimensional vector, and so this vector, delta x alpha, can be labeled, it's quite natural to label this using the null coordinates in this picture. So I'll pick null coordinates such that this is x minus and this is x plus. Okay, and so this deformation gives me some region some D of B, some domain of dependence of this B cut here. But you should always remember that this is a function of y. So as a function of y, it's going to wiggle around, and so there really is no symmetry associated to this region. Okay. All right. So so the goal is to compute the deformation, the change in the modular Hamiltonian under this deformation, which is KB minus KA. Of course, to make sense of this, we always have to go to the full modular Hamiltonian, because otherwise this operator doesn't make much sense. It is divergent and so forth. So I should put hats on this. And so what is this? At first order. Okay, so the strategy will, we want to do a calculation, so we have to, at some point we have to use, say, Euclidean methods to write a path integral for the density matrix. So at an intermediate step, I'll be talking about the non-full modular Hamiltonian, and then at the end of the day, we'll take the difference and hope that we get something finite. So we need to do a Euclidean path integral. And I should have said, these modular Hamiltonians are all for the vacuum. Okay. We could, it's a more non-trivial problem to do it for some other state, but you could try to do that. Okay, so we have some Euclidean path integral, and it's the same Euclidean path integral as before in the undeformed case. So this is undeformed now, where we include sort of a branch cut here. And again, I'm just showing 2 dimensions, but the y direction always factors out. And so we do the path integral here with different boundary conditions on the top and the bottom, and that produces a density matrix for us. Right, and in particular, then we're going to sort of think about angular evolution in this direction. Okay. Okay, but now what we want is we want to deform this cut a little bit in some direction. Now, we're working in Euclidean, so what we're actually going to do is we're going to sort of deform the boundary of the entangling surface, which is here, in some general Euclidean direction, which is not quite the picture that we want, but at the end of the day, what we're going to do is just wick rotate back in terms of the deformation. So the deformation will be in Euclidean, will be some shape deformation in Euclidean, and then we'll do some analytic continuation to get the real-time picture here. Okay, so that means that we need a new cut, which is where we're going to put our entangling surface, that's somewhere up here, and then we can sort of do whatever we like with where we put the branch cut. And so this is this is for the undeformed case, and this is the deformed sigma b, and this is sigma a. Okay, so it's okay. So in principle, this is enough. So we just need to do the path integral on this plane with some funny boundary conditions on this sort of moving cut here. And if we can do that, then we can compute the density matrix. It's not very convenient to try to work in this picture. Rather, what you can do is you can basically just pick a different coordinate system for the deformed region such that there is no deformation. So we just push this back here. So what we're really doing is we're doing a diffeomorphism, which is just a coordinate change. And that diffeomorphism comes with some vector field. And the vector field is defined everywhere in this plane. And we're going to apply that to this picture. And what we get is, for the yellow region, just again, a flat cut. However, the difference is, because we've applied this diffeomorphism, in this new coordinate system, we have a metric which is different. So we have to change the metric. So in particular, we'll have a region in here which we can take to be compact, where there's a new metric. So the change in the metric is then given by the usual formula for diffeomorphism. Okay. And this is convenient because now we can easily sort of do perturbations in this metric rather than having to do something funny here. Okay, and so this becomes very much just like the picture that we had for the scalar perturbations that I talked about last time. To generate this density matrix, you now do a path integral. Okay, you can think about slicing the path integral in the angular direction. And the only difference between this and the vacuum case is that now you have to include some metric when you do that, some non-trivial metric. Okay, so and the metric couples to the stress tensor in a quantum field theory. So then we can just perturb in that metric, and then we'll just bring down factors of the stress tensor, and we'll get correlation functions of the stress tensor and so forth. So this is kind of, instead of doing scalar perturbations, now we're doing stress tensor perturbations. So can do shape deformations by deforming the path integral by some insertion of the stress tensor multiplying this metric. Okay. And so in the unperturbed side, we have some density matrix associated to region A. Sorry, what do I want to say? So on the left-hand side, for the yellow cut, we have some density matrix associated to the region B, which is sort of what we wanted to compute. And the metric here is just flat. So in Euclidean, it's just a conic to delta, like here. And we're going to replace that with a new density matrix for the region A, so the undeformed region in this picture, but with a non-trivial metric. Delta plus H delta G. Bad notation. Okay. And this guy then, you can rewrite, roughly speaking, as the undeformed density matrix, sigma A, for the flat metric, times some angular ordered contribution from the stress tensor. So this is the usual trick of passing from the path integral to some operator formalism. Okay, and then then we go through the same procedure. Now we can we can expand in this guy, and that will give an expansion in the density matrix. Okay. Okay, so we can expand similarly. B, sigma A, plus some delta sigma. Sorry. Let me call this sigma A. Okay, and now, so what do we want to compute? Well, we want to get some access to the modular Hamiltonian. So it's an operator, but we want to calculate something. So let's just calculate matrix elements of that operator. So let's just pick a state and compute the expectation value of the operator in the state, and that will at least give us the diagonal elements, and you can work out the off-diagonal elements. Okay. Here. compute the modular Hamiltonian in some state, some excited state. Okay. So for example, in the density matrix language, we would like to compute the trace over some excited, this is the excited state, and then the log of the reduced density matrix for the vacuum. So this is just the modular Hamiltonian up to some factors. Okay, so that's what we'd like to calculate. And one trick that we can use is the statement that we should be able to do this calculation with respect to this picture. This calculation is sort of written in this picture, if we could do that calculation. We can map it to this picture just by changing the metric. So this becomes trace over rho A in the presence of some deformation times log sigma A in the presence of some deformation. And so we need to do the deformation for both density matrices because we're changing the region for both density matrices. Okay, so then this is easier to work with because the region is A, and this is what we're going to expand. Okay. So now you can go through this calculation. There's clearly two terms that you're going to get when you linearize. There's a term that comes from here, and there's a term that comes from here. And they both contribute, although they won't both contribute to the final answer. But at the end of the day, you get some expression for this guy, which is an integral over this deformation. So the change in the metric. Let me write it. Good. And it's an integral over this region. So I do this I should have said this, I do this diffeomorphism to go from this picture to this picture, and it's only non-zero in some finite region around here, and I sort of smoothly set it to 0 out here. Okay. And then you get two terms, one which I'll call z mu nu 1, and then this blue one, z mu nu 2. Okay, and they're multiplying this metric. And okay, so there's some tricks here that you can use that we didn't actually use in the paper, but it's sort of more convenient to do it this way. So the trick is that you can show various properties of the sum of these two, and then all we'll need to do is to find the behavior of these so this is integrated over the metric as a function of x, and these are all defined at some point x. And so we need to understand the behavior of these functions as x goes to the origin, and that will give the main contribution. Okay, so let me go through that. So the two terms are exactly the two kinds of terms that we saw for the scalar case. So we get some term, which you might call the modular energy term, the modular Hamiltonian term. So it's kind of like the first law term. And the second term is, again, some integral over modular flow, my favorite kernel, some I epsilon here, and then we have modular flow of the stress tensor. Okay, so where does this come from? Well, this just comes from expanding the log. So the second term is the expansion of the log, and as I said before, it's subtle to expand. To do it, when you do it properly, you find this modular flow, just like in the scalar case. Okay. So this comes from expanding log sigma A plus delta rho. And so these two terms have various properties. The first term is divergent. So there's divergences associated with the first term. That's because this operator is not the full modular Hamiltonian, and so it's a bad operator. Okay, so it has divergences, especially as x comes to the boundary of the region. Whereas this term is finite. So this term is fine. But together they sort of satisfy nice properties. The first one is that, nice properties. The first one is that if I sum the two terms, this whole function is single valued in the x-plane. It's actually not obvious from this expression. I've actually only given you the expression which is true when x is evaluated in the domain of dependence of A. When x is evaluated elsewhere, especially in this Euclidean plane, you get slightly different expressions. But then you can show with those expressions that the answer is single valued. And you can also show the second property is you can show that the sum of the two terms is conserved, 0. And that's just because they both involve the stress tensor insertion, and the stress tensor is conserved as long as you're away from any operator insertions, and that is true. So it turns out that these two properties mean that we can evaluate this integral just by analyzing the behavior of this function as x goes to the boundary of A. So let me do that now, and then we'll see the answer pop out. So we're going to take x in the domain of dependence of A. So we're sort of now wick rotating back to real time. We have the allocation of the stress tensor inserted here, and we're going to take a limit towards the origin here. And as you take that limit, well, what does modular flow do? This is modular flow with respect to the undeformed region, so it's just a boost. So it just boosts this operator around. However, because of the indices on the stress tensor, you get various factors. So modular flow on the stress tensor, if I write it in the null, for the null components, you pick up a factor which goes like this. And this enhancement, e to the 2s, is going to be important, and is where the answer will come from. So the idea is that if I just took x to the origin, and at finite s, then I would get something which is just finite. However, there's an enhancement from the s integral, from this modular flow integral, which gives a new contribution.
What did you say that outside the boundary is not into 0? Why are you taking the limit?
Why am I taking this limit? It's because it's conserved. So it's 0 here. And because this is a diffeomorphism, I can integrate by parts, and it gives 0. So the only possible contribution comes from the origin. What should say? Okay. This is away from x, away from boundary of A. So you get this. Okay. So this is how modular flow acts on the null components of the stress tensor. And so what we examine is the large S limit of this integral. Okay? And so you get various factors. You get some integral up to infinity. The kernel, this kernel just becomes e to the minus s. You get this e to the 2s here. Then you get t minus minus, x minus e to the s. But because we're boosting to large S, one of the null coordinates goes to 0 in the stress tensor insertion. So you just evaluate it 0. X plus 0. And this is from some S star, which is large enough. And so then all we have to do is do some redefinitions. So we take lambda to be x minus e to the s. And as we send x minus to 0, we find that this behaves like there's a pole, 1 over x minus pole, which just comes from putting this in. There's an integral over d lambda from 0 to minus infinity, t minus minus, lambda 0, evaluated in the excited state row. Okay. So this pole is going to give us the answer, and that's just because we're going to plug this answer into here, and we're going to integrate by parts on the diffeomorphism. So, G mu. And the derivative acting on this function is just going to give us a delta function. Okay, and that delta function is going to give the answer. Okay. So over here. Okay, so still integrate. We still need to integrate over this function, this z mu nu function that we've just figured out. So this is the, I should have said, this is the z minus minus component of this function, z minus minus. And so we need to integrate z mu nu. But now we can we can do the integral in this region, and it's single valued. It's single valued because of the property that I told you. You can prove that. It's a little bit more non-trivial to prove. Actually, the proof of the fact that this is single valued is basically the KMS condition. So that also is playing a role here. Okay, but then we take this answer, we have to integrate it in Euclidean. So this is the Euclidean plane, W. So we need to Wick rotate back. So x plus or minus are going to go to W bar. And then this 1 over x minus is just some pole. And then we can use these representations of the delta function up to some numbers, which you might be familiar with from CFD, from 2D CFD, etc. And so then we find the answer for the shape deformation of the modular energy in the excited state. So this is for the vacuum, remember? Is, well, I factored out the y integral, but let's put it back. So we have the y integral. The delta function gives a contribution from the shape deformation at the origin. And what is the shape deformation of the origin? It's the deformation that we're interested in, which is just delta x plus. You get the expectation value of this operator here. I'm doing plus here. Sorry, this operator, let me do minus. But this is just what I'll call a null energy operator. So I'll call it epsilon minus null energy operator plus delta x plus epsilon plus. Okay. All right. So we've got to the answer. I just want to point out where it came from. It came from this modular flow argument at large modular flow. And so what's happening is this operator is coming close to the origin, but it's also being boosted by this large S. And the end result is just an operator which is integrated on the future part of the Rindler horizon. Okay. So it's a funny fact about this perturbation theory and for entanglement that you get these kinds of things, these null energy operators, sort of naturally coming out. And so we can use this fact to extract a new modular Hamiltonian. So extract, I should have said, this is all plus divergences. And these divergences come from the other term. So I just analyzed one of the terms in that limit, but the other term has potential divergences. However, you can show that when you compute the difference between this and the complement region, those divergences exactly cancel, and you're just left with this term, which then just becomes an integral over y, delta x minus y. Remember, these are functions of y, times this null energy operator, now extended from minus infinity to infinity, plus minus goes to plus. Okay, so this is the final answer. Yeah, it depends on the theory a little bit, because what's happening is that in this other term, so it's that term, the first term, the stress tensor is coming close to the modular Hamiltonian, but it's a half modular Hamiltonian. So that also has a stress tensor in it, so you get new operators that arise, and they sit right on the entangling surface. Okay, and they depend on the dimension of the operator. You get divergences that depend on that. Yes?
So you said the sum of these two terms is single valued, but now you were just integrating Z2? Why was that still single valued?
It's because the divergence doesn't change that fact. Sorry, the full thing is single valued. I use that to integrate by parts, but then the only interesting contribution comes from Z2. Yeah, that's right. Yeah. Good. Okay, and so in this expression, because we sort of did perturbation theory for this region here, but the complement region gives us the other half of the operator. So you just get the full null energy operator. Okay. So it's quite nice that this modular Hamiltonian is now sensitive to this null energy, and this is exactly the average null energy operator that I said we were sort of trying to prove. Okay, now this is an expansion. So we did this perturbatively. So in principle, you could carry it out to higher orders in the expansion and so forth. However, there's a special case. Special case where I just consider deforming the region. Right now I'm just deforming it in any random direction. As long as it's contained within the dependence of A, that's okay. But now I can consider a null deformation. So let me set delta x plus of y to be 0. Then I only get a contribution from this term. There is no this term. So this is the other term, but now I'm just doing this null deformation like this. And this is exactly the case that was shown recently by Horacio and company to be exact. So this expression for the modular Hamiltonian, even though in principle maybe there could have been higher order corrections, it's in fact exact. And I find this really fascinating, and maybe this has been discussed before, but let me just sort of explain it a little bit, how you show this. So in this picture, in this situation, this is the picture. We have our two regions. The original region, which is the A cut, and then the deformed region, but now the deformation is happening in this null direction here. Okay, and so this is my new region. And this region is defined by this deformation vector. And again, it's important, and I emphasize, that this deformation vector depends on y in the directions coming out of the board. If it was a constant independent of y, then this would also be a Rindler cut, and then we would know what the modular Hamiltonian is. And of course, it is consistent with this result, because I just have to set this, and it's correct. So in this situation, you have two domains of dependence. So we have d of A, d of B, and this is sort of the picture that I drew in the first class, where you have these domains included. So this is an inclusion. Okay, and so this happens typically, but in some situations, it can be shown that if I do modular evolution of one of these regions, so that means I'm just taking this whole region and I'm imagining, or really I should talk about the algebra. I'm imagining taking the algebra of operators and flowing with them. Then if this guy is contained within itself for positive S, then this is the situation. So this is just an inclusion. This is called a half-sided inclusion. And in this case, it's true because this was a Rindler cut. Okay, so Rindler cuts have geometric modular Hamiltonians. So you know what they do to the operators just by pictures, right? By how they flow in terms of pictures. And what does this do? This is a boost. The A modular Hamiltonian is a boost. So it just boosts this region in like this. And because this region is exactly on the null direction here, it actually boosts it into itself. Okay, if it wasn't, so if we went back to the generic situation when we started doing perturbation theory, which looked more like this. Generic situation is where the inclusion, it's still an inclusion, but looks like this, and the deformation is not null. Then what happens if I act with this region with the boost of this guy? Well, this point gets boosted, and so we get another wedge. But you see there's a region that's not contained in the original region. Okay, so this is not half-sided modular inclusion. So it's only when you have this null deformation is this true. But it turns out that this is a sufficient condition to prove that the modular Hamiltonians of the vacuum case satisfies an algebra. So we can then prove Ka hat Kb is I Kb. Okay. So some intuition behind this algebra. Well, if I did take this to be a Rindler cut, B to be a Rindler cut, then these are boost operators. They're both boost operators. And the right-hand side, the difference between the boost operators is just the deformation, which is now uniform. It's independent of Y, times the null energy operator, which of course is just a null translation. So this gives a null translation. And then this is just if you think about Lorentz transformations, this is just true. This is just satisfied by the algebra of Lorentz transformation. So this is sort of simply true. But the fascinating thing that these people in algebraic quantum field theory, Weissenbrock and Borchers, what they proved is that to have this kind of an algebra, the sufficient condition is this inclusion. And that's all you need. And the thing is, this is exactly the situation where we have a non-trivial null deformation, where it's still true, so that means this is a highly non-trivial algebra in that case, this fact. Okay. And I should say a few words about how they, well, I'm not going to say how they prove it, but I just want to put it out there that the proof of this is ridiculous. It involves all of these things that I've been telling you about, KMS conditions, modular flow, analyticity in the S-plane. It's all important and highly non-trivial. Okay, so this is obvious, but this is not obvious. But then, basically, once you have this algebra, you can take, well, one way to prove that this is an exact result is to take this as if it was perturbatively true, apply this algebra, basically bootstrap this perturbative answer up to a full non-perturbative answer using that algebra, and then you can just show that this is true in general. Okay. Yes? I haven't tried to do these second order calculations, so I'm not sure. I mean, in some sense, they sort of can't be there by symmetries and various arguments like that, because there's just no operator you can put here. That's the only operator. So that's sort of a quick argument for this. Okay. But one thing to say is that there will definitely be second order terms when you have two null deformations that are in the opposite directions. Then there'll definitely be cross terms, and you could try to calculate them. Okay. So let me just box the answer. So the modular Hamiltonian associated to the B region, if I just sort of add them together now, I was just writing the perturbation, but let me add them together, is the integral x minus t minus minus evaluated at x minus x plus 0 and y. Okay, so let me box this. And so this is a new modular Hamiltonian. So I want to sort of emphasize that this is really a new modular Hamiltonian. It hasn't been used as much as the other modular Hamiltonian for the sort of the local Rindler case. So there's likely a lot of things that we can learn from this. The other thing to say is the name, I guess. So you might call this a local modular Hamiltonian because it's integral over the stress tensor. So it looks like a local integral of the stress tensor. It's probably a bad name because this is quite different to the other modular Hamiltonian where we know the answer. The other modular Hamiltonian, I didn't really write it out explicitly at any point, but I wrote it in this form. Remember, I wrote it in this form where we imagined we had some killing vector associated to the symmetry that holds fixed the entangling surface. Then you just write it like this. And as I said, you could sort of integrate this at any point in the wedge. And it didn't matter because the stress tensor is inconserved. And this is a killing vector, so I can just integrate it anywhere. But I could choose to integrate it along here. And when you do that, you can take the limits and so forth. So C in particular has a term that looks like this, plus or minus x plus d plus, and this guy goes away in that limit because I'm setting this is x minus. I'm setting x plus to 0, so that guy goes away. This normal vector, well, the normal vector of a surface in a relativistic setting actually looks like this. So as you boost the normal vector towards this direction, it also points in that direction. So then this just gives you t minus minus x minus dx minus. Well, I was doing the half version, so infinity. And so this is the same as this. However, in this situation, I can't push this integral back because it's not a conserved charge. I can't just. So that means that if I want to use this to flow operators, the flow associated with this, the modular flow, will be non-local. So in that sense, it's still a non-local answer. Modular flow. Good. All right, so let's see one implication of this modular Hamiltonian. So the implication is, as I've suggested, a proof of the ANEC, so the average null energy condition. Okay, so the average null energy condition is the statement that integral t minus minus it should be positive. So as in, you can read this as an operator statement. I've written this this is in Minkowski space. I'm thinking of just integrating along a null curve in Minkowski space. But the original discussion of the average null energy condition is some constraint on the integral of the null components of the stress tensor integrated over a null geodesic in some spacetime. Okay, so this is one example. So we're just doing it in Minkowski space, but you can formulate it in curve space. However, it's not really true in curve space. There are examples where you can easily violate it. One example is if I put the theory on a cylinder, then you get a negative Casimir energy. And then the average null energy condition is just integrating a null geodesic around here. So you're just integrating up this negative answer. So this is a violation in curve space. But as is always the case with these things, it's a moving target. So then people have defined something called the achronal average null energy condition, which says that you only apply the average null energy condition to null geodesics which don't have time points that are 2 points on the same null geodesic that are time-like separated. So this is not the case because I can go in here, because I can go from there to there in some time-like direction. But yeah, I'm not sure how useful it is extending this. However, it is a non-trivial statement in Minkowski space, and it's believed to be true. Sorry? Say that again? Almost all the GR theorems that use the ANAC, the achronal ANAC device. Sure, but I somehow thought that one way, well, maybe I shouldn't say this because I'm not that. I feel like your quantum null energy condition is superior, and that's what we should think about. That's my feeling on this subject. Okay.
So can you generalize this to this ANAC?
No. So the argument that I'm going to give is very specific, and that's kind of why I don't like thinking about generalizing the ANAC in any case. It applies to Minkowski space because we had this symmetry to begin with. We had this rotation symmetry, and we could perturb around that. But there are other situations where you can use the same method. For example, if you have an eternal black hole or something, then you have some killing symmetry associated to that black hole, and you can use the same methods to prove the ANAC for null generators on the black hole horizon, just those generators. So you can, there are other things you can do with this, but not everything. Yes?
Is it plausible that instead of non-negativity, you get a lower bound in curved space?
A lower bound. I'm not sure. I don't really want to speculate. Sorry. Yeah. Okay. So how do we go about proving this? Well, it's sort of a neat argument that actually, okay, there has a long history. But for me, I first read about it in a paper by Blanco and Cassini. But Aaron Wall, I think, has been talking about similar arguments for quite some time. And probably, I'm not sure. Okay, so the argument is related to relative entropy. Okay, so remember I sort of told you a little bit about relative entropy. But the relative entropy is, okay, so it's a good quantity. It's one of these things you can define nicely in quantum field theory. And it tells you about the distinguishability of two states, of two density matrices. So, right. And in particular, it's bigger than 0, so, and it's 0 only when they're exactly the same. The density matrices are exactly the same. But there's one more important thing that it satisfies, which Aaron mentioned, which is monotonicity. Which is this situation where we have this inclusion. So we have some algebra of operators associated to some region B contained within the algebra of operators of A. So that this situation, we have the two wedges included in each other. If you believe that this is related to the distinguishability of two different density matrices, then it means that if I have less stuff to distinguish the two, then the relative entropy has to go down. Okay. All right. Let me just say that again. If there's less ways for you to distinguish two density matrices, then any measure on the distinguishability should decrease. Okay. So SREL decreases under inclusion. And so an example, let's do it in this context where we have these two null wedges like this. And we imagine that in this situation there's some very high momentum particle moving along in this direction, which is the excitation, and otherwise it's vacuum. Then to any observations in this region, you're not going to be able to distinguish this from vacuum, so the relative entropy should go to 0, whereas in this region you have access to this excitation, so the relative entropy will be non-zero, and so it has to decrease as you go from here to here. Okay. Some matter, which is the rho state. Okay, so just in equations, let me write it out. A okay, now proving this is kind of non-trivial, although it's doable. It's non-trivial. Perhaps you've heard that strong subadditivity is a hard thing to prove about entanglement entropy. The hardness is about the same. I'm not sure how to quantify that, but yeah, it's certainly a powerful constraint, and it has had many applications. And so it's really interesting that these applications, are related to nice things we can say about quantum field theory. And as I'll say after that in a little bit, it's also interesting. It's really related to nice things we can say about general relativity and black holes. Okay, so once we have this inequality, remember we had this form for the relative entropy as a change in the expectation value of the modular Hamiltonian for the state sigma minus the change in the entropy for the two different states. So the change just means evaluate this modular Hamiltonian in the two different states. And I think I've been carrying around a 2 pi here. Reasons, I'm not sure. Okay, so then we plug that into here. Fine. Change minus change got the sign right here. Yes. Yes. Okay, and then we use the form for the modular Hamiltonian, which okay. So at this point, what I'm gonna do is something that is okay, although ultimately it's not necessarily for the average null energy condition. But what I'm going to do is I'm going to take this expression for the full modular Hamiltonian and just guess the expression for the half modular Hamiltonian as just being the same expression, but where now I integrate from delta x minus to infinity. And that makes sense because the same kernel, and that makes sense because the full modular Hamiltonian is a difference of two modular Hamiltonians, and each one acts within the region. And the stress tensor here is only acting, this part of the integral is only acting within the B region. Okay. So if we take that and we plug it into here, then and then we do a small deformation. So we're imagining a situation where this deformation is small. Then you can expand, and this gives the fact that delta x minus of y integrated over y, 2 pi x minus 0 infinity, t minus minus, x minus evaluated in the state rho, plus the functional derivative of the change in the entanglement entropy. So this should be bigger than 0. So I'm including functional derivatives and so forth because I'm imagining doing a small deformation, and I'm thinking of this, the entropy as being determined it's a function of this deformation. So this x minus, and so to expand this, I should take a functional derivative and integrate. Okay. And so because, so this is true if this function is positive at all locations, right? Because we need this inclusion condition. So it can't be the case that delta x minus goes negative at any point, because then you don't have inclusion. So this has to be positive. So that means that this should be positive, and not only the integral is positive, but at each point y, it should be positive. Okay, so we went from something which is an integral over the y direction to something local, and we managed to do that because we made this function local, right? And that was, sort of the key to, the new step is that we have this modular Hamiltonian for these non-trivial deformations. Okay. Okay, and so the inequality that you get here well, one thing you can do is so this is a change in the entropy, which is the entanglement entropy of the excited state minus the entanglement entropy of the vacuum state. But, these things are somewhat divergent. However, you can argue that the functional derivative in the null direction of the vacuum part of this is 0, basically by relativistic invariance, by boost invariance. So if you manage to regulate the entropy in a way that is boost invariant, that should be true. And so I can drop the change, and then I just get this guy. X minus y is positive. And so this is sometimes called the half ANEC. I think it has other names, but let me call it the half ANEC. So it's a constraint on half of the integral of the stress tensor plus some contribution from the derivative of the entanglement entropy. Okay. So this is a half ANEC, and it follows from monotonicity of relative entropy. But now we can just we can apply the exact same argument, but to the opposite deformation. Okay. So sorry, to the complement region is what I should have said. The only difference being that in the complement, the inclusion goes the other way because you're still deforming in the same direction. So that means that the algebra of the complement region is contained within of A is contained within the algebra of the complement region of B. So this is sort of an opposite inclusion. And that means that various things will go the other way. And you find this, that gives rise to the following inequality, which is this minus functional derivative, the entanglement entropy for the complement region. This should be positive. And so what we can do now is I haven't really been too specific about the state, but this, sorry, I should say this is rho B. But now what we're going to do is we're just going to take the state to be pure, and if the state is pure, the entanglement entropy of the region B, so pure rho in the total space, that means the entanglement entropy of B is the same as the complement, and so that these things are the same, and so I can just add these two inequalities, and the result is I can drop the 2 pi now, is just the ANEC. Evaluated in a pure state. However, because this pure state can be any state, this argument applies to any state. That means that you can just say this as an operator statement, and that means that it also applies for mixed states. The null energy operator with a hat, which for me means the full null energy operator, is a positive semi-definite operator. Okay. All right, so that's the proof of the ANEC. So let me, I think my index should be down. Okay, questions about this? Oh, when I've given this argument before, I've done it together. One thing you can derive at a different step is that it's always true that if you have some inclusion like this, and actually this doesn't depend on the state, it doesn't have to be vacuum or anything. This operator, let me get this right. I think it's this one, is a positive operator. So this is some general way to derive positive operators in quantum field theory, which is sort of interesting. In this case, it's the ANEC. Okay. Any other questions? Okay. Yeah, it all comes from this formula. Yeah. This formula, no, you actually don't need this formula to derive this fact, because you can just use the perturbative answer. So it just relies on the perturbative answer. Because there could be corrections to this, but the perturbative answer always controls the inequality if there's some inequality. So, the leading term. So this allows you to show that this is exact for all deformation, for large deformations.
Yeah, but can you just read that in one shot? Somehow when you identify KV minus KA with P minus.
You want to derive the positivity?
Yeah.
Likely, I forget. Actually, I'm not sure if it's obvious. Maybe. Okay, so, all right, let me give some properties of this guy now. Okay, so one sort of trivial thing, and you can derive this in various ways. But the null energy operator annihilates the vacuum. Right. And so one way to see that is because this is related to this difference that I wrote there in full modular Hamiltonians. And each one of these annihilates the vacuum because they're all associated to the defining state. They're all associated to the vacuum state. And this was, remember, an important property of full modular Hamiltonians. So that's true. The content of the ANEC is non-trivial. Constrains CFTs, for example. So this Minkowski, let me say, in flat space. Because you might have thought in flat space it was trivial for some reason, and maybe it's better in curved space, but actually it's non-trivial. So it leads to these non-trivial constraints on CFTs, in particular local CFT data, which is, the usual stuff. So to describe, for example, correlation functions in a CFT of local operators, you should know the spectrum of operators, their dimensions, and their OPE coefficients between 3 of them. And then that's enough to determine all of the local correlation functions in theory. But it turns out that this ANEC gives non-trivial constraints on that. And this is the idea of Hoffman-Maldacena, where they kind of assumed the ANEC and then derived what its consequences were. And so they looked at states which were well, there were smeared versions of this, but basically local operators like some scalar operator, some current, some stress tensor acting on the vacuum, and call this the state psi. And then they computed this null energy operator in the state. Right. And it's not hard to see because this is one operator acting on the vacuum. This is a 3-point function. Because there's a stress tensor in here, and there's one operator in the bra and the cat. Okay? And what 3-point functions do you get? Well, so you get 3-point functions, 3-point OPE coefficients, this data. For example, you get C, O, O, T. So you always get two operators in a stress, or these operators don't need to be the same, but there's always a stress tensor. And so, you get JJT, CTTT. Well, sorry, I shouldn't say it like this. I need to say it like this. You get 3-point functions. 3-point functions in CFTs are determined up to symmetries by some numbers. Okay, so that's why you're constraining these numbers. These are the OP coefficients. But actually, this only gives you a non-trivial constraint, only non-trivial, if you have the situation, which is not true for this guy, where what you can write down for the 3-point function, you can write down multiple invariant structures, and each one of them comes with a coefficient. So this is some invariant. So these are some invariant structures, and the reason you can do this is because there are indices on these objects. So there are multiple ways to make conformally invariant structures out of those indices. The ANEC sort of gives bounds between the various alphas and betas. And it doesn't work in this case because this is determined by, if it's a scalar operator, this is determined by a single structure. And then I can integrate the ANEC. And the integral of the ANEC is just positivity of energy, right? If I integrate it over the transverse directions, I get positivity of the null energy, and that's just some constraint we've known forever. So it's not, ANAC is no longer trivial, is trivial in that case. Okay. All right. Let's see. Okay, so let me let me say a few things about this. So so all right, so one thing that's a little bit funny is that, okay, so the ANAC is interesting and non-trivial in flat space, but you know, it really, the ANAC came from gravitational physics, from thinking about general relativity. In particular, thinking about general relativity coupled, say, semi-classically to quantum field theory. And so, for example, you know, if you have an eternal black hole, then a constraint that you might want to impose on this black hole is that even in the presence of matter, say some quantum field theory matter, there's no way for you to send signals from the two asymptotic regions of this eternal black hole. So black holes, not traversable, follows from the ANAC. Now it's the ANAC in curved space, but actually it's the ANAC that we can still derive because it's integrated along this killing horizon, and these methods can be generalized to that situation. Okay, and so there's this. Okay, so so the ANAC was conjectured based on this fact, but you know there's this seeming disconnect between this proof that I just gave you, which says nothing about gravity. It's just about quantum field theory, and seemingly there's nothing about gravity. And so how are they connected? And it turns out that the connection comes from thinking about this generalized entropy. So the generalized entropy is an entropy you can associate to a black hole horizon. So this is the horizon of the black hole. The usual entropy you would associate to a horizon is just the area of the black hole divided by 4g newtons, so that's well known. But there's various reasons why we shouldn't expect this to be the final answer. In particular, it seems that the correct thing to do is to take the entanglement entropy of some fields, where in this sort of situation, we would think about some Cauchy slice in this black hole background, and we would split the Cauchy slice into A and A complement, and then we would think about the entanglement entropy of matter fields in this region. And then it's natural to add that to the area of the black hole. Okay. And so the motivation for this comes from something called the generalized second law. And this is kind of the idea that, okay, so if you have, if you just look at classical gravitational physics, then you can prove that the area of a black hole under some reasonable assumptions is always increasing. So this looks like a second law, and that's the second law of black hole thermodynamics. But then you can sort of imagine some thought experiments where you take some stuff, some matter, and you throw it into the black hole, and there's some entropy associated to that matter, and it's gone. As soon as you throw it into the black hole, somehow it's missing, and so you seemingly violated the usual second law of thermodynamics, but the idea is you can fix this by adding these two together, and then whenever you throw in the matter to the black hole, you lose the matter, but then the area of the black hole increases because you've added some energy to the black hole. And so this is the idea of the generalized second law. To make it precise, okay, so that's the situation, well, where I had some matter here and I threw it in. But really, to talk about this in terms of quantum fields, we should pick something which isn't the entropy of matter, because we don't really know how to define that. But it seems like the entanglement entropy is a good quantity. In particular, if I take two slices, this slice and a later slice, then exactly for the same reason, you know, the same picture that I was drawing before, you sort of lose the information of this matter at later time. And so that's like the entanglement entropy decreasing, yet the area of the black hole will increase to compensate. And that's the statement of this generalized second law. Okay. So this picture is familiar, right? So in particular, you can let's just model the black hole horizon as Rindler space. So locally, the black hole horizon, or close to the horizon, it looks like Rindler space. And so we can just sort of, black hole horizon, the Rindler horizon. And then, you know, our pictures that we were drawing look very similar. So this is now the horizon of a black hole. And then we have two slices, or we have two cuts here. And then if we had some matter and threw it in, then the entanglement entropy would decrease. But the area is meant to increase to compensate. Of course, we can sort of apply this in flat space. We can imagine thinking about gravity in flat space coupled to the quantum field theory that I was talking to you about, and sort of computing the back reaction of the quantum field theory to leading order, and that's this sort of semi-classical limit. Okay. So, right. So I didn't say what the generalized second law is, but it's that this generalized entropy should increase along horizons, along these causal horizons. Okay. So now it turns out that this statement, I think I erased it. Yeah. So the statement of the half average null energy condition in the limit where I take the semi-classical limit where I take the quantum field theory and I couple it to gravity, can be interpreted exactly as the generalized second law. So the half Enoch as the generalized second law. And I'm not going to go through the details in lieu of time, but basically the generalized entropy gets mapped to this relative entropy plus some constant. And the relative entropy, remember, well, right, and then the generalized second, you apply the generalized second law for small perturbations greater than 0, and then that just becomes this monotonicity of relative entropy. There's a minus sign here because the generalized entropy should increase, but the relative entropy should decrease because the state becomes less distinguishable from the vacuum. And so then the two terms in the half Enoch looked like, integral d lambda t minus minus 0 to infinity plus the shape deformation of entanglement should be bigger than 0. And so this is obviously the term in the generalized entropy, which is here, whereas the integral of the stress tensor comes from just solving Einstein's equations. And so this is the back reaction of the stress tensor on the metric in the bulk, and that changes the area, and it exactly changes the area by this much. Okay. So really, these statements are intimately related to gravitational physics in this semi-classical limit. So let me say a few words about the quantum null energy condition, and then I finish up. Okay, so the quantum null energy condition arises from a sort of a similar gravitational argument as this. However, instead of demanding that something about the change in the generalized entropy as I sort of deform along the horizon, what I demand is something about how the generalized entropy changes as a second derivative as I deform along the horizon. And this is related to quantum focusing. But then when I take the flat space limit, I get this constraint that t minus minus in my state, 2 pi, should be bigger than the second derivative of this functional derivative of the entanglement entropy. And so this is a question mark, right? So this is a conjecture based on gravitational physics, based on this quantum focusing condition, and then you look at it in flat space, and it just becomes this statement. And it's not hard, it's somewhat related to this statement. It's like a derivative of this statement where the inequality goes the other way. So to prove it, seemingly what we need, just like this comes from monotonicity of relative entropy, we need some non-trivial statement about the second derivative of relative entropy. So the second shape derivative. So that, there's no quantum information object that does that. So it seems like maybe it's wrong. Maybe you can find counterexamples and so forth. In a recent paper I just want to mention this because it sort of brings together a lot of these methods that I've been talking about. It's nice to end on this with Srivatsan, with Raja Wong, and Zuhair Kanka. We proved this flat space version of the quantum null energy condition, and our proof involved modular flow in a very non-trivial way, I think. And it's a sort of a similar setup as to this, the setup where we proved the half ANEC, except now you think about two regions which are causally separated so that you don't have this inclusion, and they're causally separated in this null direction. I mean, they're only just causally separated in this null direction. So we have some algebra of operators associated to some B region, some algebra of operators associated to what would have been before we were talking about the A region, and there was some inclusion, but now if I take the complement of that, I get a wedge over here. And it's and as I said, there's a basic constraint on these algebras that if they're space-like separated, then these two algebras should commute. So if you're worried about this null, the fact that there's a null direction here, then you can deform it just a little bit inwards so that they're space-like separated. So this is this is the statement of causality in this situation. And if you try to use local operators, you can prove the average null energy condition. However, if you use local operators including modular flow. So we take some operator in this region, we mix it up with this region by applying modular flow, so this S operation, and we're going to flow this guy with respect to the modular Hamiltonian of the excited state. So this is the new non-trivial thing. And then we'll take an operator in the B region and we'll flow it with respect to the B modular Hamiltonian of the excited state. And these should still commute, these operators, because the action of modular flow, as I told you, at least for real S, is such that it leaves you within this algebra. Okay? So you think of this as some complicated operator over here, some complicated operator over here, but they're still within these causal wedges, and so they should still commute. Now, one piece of intuition for why this might be the right thing to do connects with what I told you before about how you can reconstruct the bulk with modular flow. So remember, last lecture, I told you how to get an operator with modular flow, and you could be very explicit if you wanted the operator to be on this Ru-Takinagi surface, which lies deep in the bulk. So how does it connect to that? Well, it turns out that if we study this constraint in holographic theories, so I'm just going to draw this same picture, but now here, and this is the z direction, then associated to this region here with this algebra, there's some entangling surface, okay? And the entangling surface, I'm just drawing 2 dimensions on the boundary, so again, the y direction is factored out. The entangling surface does something like this in the bulk as you fall in. So this is the RT surface for A, and this is the RT surface for B. And associated to those surfaces is this thing that she was telling you about, which is the entanglement wedge. So there's some entanglement wedge associated to the complement region here, and that associated to A here. And this, roughly speaking, is some space-time region that lies between the RT surface and the domain of dependence on the boundary. Okay. Similarly here, this region is defined like that. Now, if you believe, so one natural question is there a way in the bulk for you to communicate between these 2 regions? So what does that mean? If I have some bulk operator phi here, call it phi B complement, and one here, phi A, can I send a signal between these 2? So does that mean, can I commute? Do these operators, do they have a non-zero commutation or not? And you can argue that this should be 0. And this argument is based on the idea of bulk reconstruction. The idea that I can rewrite bulk operators, maybe in some highly complicated way, in this entanglement wedge region as operators just acting in here, and similarly over here. Okay, but then if I can do that with these operators, then it's impossible for them to have a non-zero commutation because these operators commute. Okay. So cannot send signals between the entanglement wedges for this, for this reason. We started off with regions on the boundary which are causally separated, and they have to be the same. There has to be the same causal separation in here. But well, how do we probe this causality? I told you we can probe these. We can make these operators. In fact, we can make operators right on the entangling surface by using modular flow. Okay, but again, it's modular flow for the state that you're interested in. So this could be some state which has some excitation in the bulk somewhere. So these RT surfaces are non-trivial, And you have to use that modular flow. Okay? And so that's why you would maybe thinking about modular flow is interesting in this context. Then the final statement, and the final reason why this likely has something to do with the QNEC itself, is that there's a very nice paper by Leichenauer. Spelled this right. I spelled it wrong. And Kohler, where they showed that this idea that these things should commute, which is called entanglement wedge nesting. Well, it's related to entanglement wedge nesting. They showed that this constraint implies applied near the boundary. So as z goes to 0 in this picture, implies the quantum null energy condition in holographic theories. So this is a special class of theories that they proved the quantum null energy condition for, and we proved it by thinking about, more generally, by thinking about more general aspects of modular flow in quantum field theory that may not have this dual picture. However, ADS CFT was very important for the idea and the inspiration for this. Okay, so I'm over time, so let me finish there.